You see thousands of tiny points of light scattered across the darkness. Some look brighter than others, some seem clustered together, and some appear isolated. Without realizing it, your brain quickly organizes this view into something simple. It imagines the stars as if they were small lights attached to a flat ceiling high above your head. But this picture is completely misleading. The stars are not placed on a flat surface. They are scattered through an enormous three-dimensional space. Some of the stars you see may be relatively nearby in cosmic terms, perhaps a few dozen light years away. Others may be hundreds or thousands of light years distant. Yet from Earth they all appear to lie on the same dark background, as if they were part of a distant painting rather than objects separated by unimaginable distances. This creates a very strange challenge for astronomers. If the universe is vast, empty, and three-dimensional, how can anyone possibly measure how far away something is? On Earth, the problem of distance is straightforward. If you want to know how far two cities are from each other, you can measure the road between them. You can use satellites orbiting the planet to calculate positions with great accuracy. You can even send a laser beam toward a reflector and measure how long it takes for the light to return. All of these methods rely on something simple, a stable environment with clear reference points. But space offers none of that. There is no solid ground connecting one star to another. There are no markers placed at regular intervals. You cannot stretch a measuring tape across the emptiness between Earth and a distant sun. Even the nearest star beyond our solar system lies about 40 trillion kilometers away, a distance so large that ordinary intuition completely fails. So astronomers must solve the problem in a completely different way. They measure distance using light. At first this sounds simple. If light travels at a constant speed, then in principle you could measure how long light takes to travel from a star to Earth. But there is an immediate problem with this idea. You cannot start a stopwatch when the light leaves the star. By the time the light arrives here, its journey is already over. What we receive from the universe is not a real time signal. It is delayed information. If a star is 100 light years away, the light reaching your eyes tonight began traveling toward Earth a century ago. That means you are not seeing the star as it exists today. You are seeing it as it existed 100 years in the past. In other words, every time you look into space, you are also looking backward through time. This makes the task of measuring distance much stranger than it first appears. Astronomers are not simply observing objects sitting quietly in space. They are observing ancient light that has been traveling across enormous distances for years, centuries, or even billions of years. The night sky is therefore not a simple picture of where things are. It is more like a collection of messages arriving from different moments in the past, each carried by a beam of light crossing the universe. Understanding this simple fact is the first step toward realizing why measuring distance in space is far more difficult than measuring anything here on Earth. One of the first reliable ways astronomers discovered to measure distances in space is based on a very simple idea that most people experience without ever thinking about it. The idea is called parallax, and it comes from the way objects appear to shift position when you observe them from different viewpoints. You can test this effect yourself with a small experiment. Hold your thumb out in front of your face at arm's length. Now close your left eye and look at your thumb with your right eye. Then switch and close your right eye while opening your left. Your thumb will appear to jump sideways against the background, but your thumb did not move at all. The only thing that changed was the position of your eye. Because your two eyes are separated by a few centimeters, each eye sees the thumb from a slightly different angle. Your brain uses that tiny difference to estimate how far away the thumb is. This is one of the main reasons humans are able to perceive depth. Astronomers realized that the same principle could be used to measure the distance to nearby stars. Instead of using two eyes, astronomers use two different positions of the Earth in its orbit around the Sun. As Earth travels around the Sun during the year, its position in space changes dramatically. 6 months apart, Earth is on opposite sides of its orbit. The distance between those two positions is about 300 million kilometers. That enormous separation creates two different viewing angles toward nearby stars. When astronomers observe a nearby star in January, and then observe the same star again in July, they find that the star appears to shift slightly against the background of much more distant stars. The distant stars are so far away that they appear almost completely fixed, while the nearby star seems to move back and forth. This tiny apparent movement is called stellar parallax. By measuring the angle of this shift and applying simple geometry, astronomers can calculate the distance to the star. The method is elegant because it does not rely on guessing brightness or making complicated assumptions. It is a direct geometric measurement. However, the difficulty lies in just how incredibly small the shift actually is. Even for relatively nearby stars, the angle of movement is extremely tiny. In many cases, the shift is less than 1 arcsecond. An arcsecond is an angle so small that it is roughly equivalent to the apparent size of a coin viewed from several kilometers away. Trying to measure such a small angle is extraordinarily difficult. For centuries, astronomers attempted to detect stellar parallax and failed. Their telescopes simply were not precise enough. It was not until the 19th century that astronomers finally succeeded in measuring the parallax of a nearby star. The moment this measurement was confirmed, it represented a major breakthrough in our understanding of the universe. For the first time, scientists had a reliable way to determine the distances to stars beyond our solar system. But this method has a severe limitation. The farther away a star is, the smaller the parallax shift becomes. As distance increases, the apparent movement shrinks so much that even the most precise instruments struggle to detect it. Eventually, the shift becomes so small that it effectively disappears into measurement uncertainty. This means parallax works beautifully for stars that are relatively close to Earth, but it quickly becomes useless for objects deeper in the galaxy. And since the universe extends far beyond the nearby stars, astronomers had to invent entirely new methods to measure distances on a much larger cosmic scale. As astronomers pushed their observations farther into space, they quickly encountered the limits of parallax. The method worked beautifully for nearby stars, but the universe did not end there. Beyond a certain distance, stars became too far away for their tiny shifts to be measured. The geometry still existed, but the angles were simply too small to detect, even with powerful telescopes. So astronomers had to find a different way to measure distance. Instead of relying on geometry alone, they began searching for objects in space that could act as reliable indicators of distance. Something like a standard light bulb whose true brightness was already known. If you know how bright something truly is, you can estimate how far away it must be by comparing that brightness to how bright it appears from your location. Imagine standing on a dark road at night and seeing a street lamp far in the distance. Even without measuring the distance directly, your brain makes an estimate. If the light looks dim, you assume it must be far away. If it appears bright, you assume it is closer. This judgment works because you already have some idea of how bright a street lamp normally is. Astronomers search the sky for objects that behave in a similarly predictable way. Eventually, they found a remarkable type of star known as a Cepheid variable. These stars do something unusual. Instead of shining with a steady brightness like most stars, they repeatedly brighten and dim in a regular cycle. The pattern is extremely consistent, almost like a cosmic heartbeat. Some Cepheid stars pulse slowly, taking many days to complete one cycle. Others pulse more quickly. The remarkable discovery was that the speed of this pulsing is directly connected to the star's true brightness. Stars that pulse slowly are naturally brighter. Stars that pulse rapidly are slightly dimmer. This relationship turned Cepheid variables into one of the most powerful measuring tools in astronomy. By observing how long it takes for a Cepheid star to brighten and dim, astronomers can determine how bright the star truly is. Once they know its real brightness, they compare that with how bright the star appears from Earth. If the star appears very dim but is known to be extremely bright, then it must be very far away. Using this simple comparison, astronomers can estimate the distance. This method allowed scientists to measure distances far beyond the reach of parallax. For the first time, astronomers could begin measuring the scale of the universe beyond the nearby neighborhood of stars. In the early 20th century, this technique led to one of the most important discoveries in astronomy. When astronomers studied faint spiral, shaped objects in the sky, Many people believed these objects were simply clouds of gas within our own galaxy. But when scientists found Cepheid variable stars inside those spirals, they measured their distances and realized something astonishing. These objects were far too distant to belong to the Milky Way. They were entire galaxies of their own. The universe suddenly became far larger than anyone had previously imagined. Instead of a single galaxy surrounded by empty space, astronomers realized the cosmos was filled with countless galaxies scattered across unimaginable distances. Each galaxy contained billions of stars, and many of those stars might host their own planets. Cepheid variables became one of the first reliable rungs on what astronomers now call the cosmic distance ladder. Each rung is a different technique used to measure distances farther and farther into space. But every rung depends on the accuracy of the previous one, and that dependence introduces new uncertainties as astronomers try to measure the truly enormous scale of the universe. As astronomers continued measuring greater and greater distances, they encountered another complication that made the problem even more confusing. It turned out that measuring distance in the universe is not only difficult because objects are far away. The deeper problem is that the universe itself is changing while the light from distant objects is traveling toward us. Space is not a fixed stage where galaxies simply sit and move around. Instead, space itself can stretch and expand. This idea was one of the most surprising discoveries in modern astronomy. When astronomers observe distant galaxies, they notice something unusual about the light coming from them. The light waves appear stretched, shifted toward the red end of the spectrum. This effect is called redshift, and it tells scientists that those galaxies are moving away from us. At first glance, it might seem like galaxies are simply flying outward through space like fragments from an explosion. But the real situation is more subtle than that. A helpful way to imagine this is by thinking about the surface of a balloon. Imagine drawing small dots on the balloon with a marker. Each dot represents a galaxy. Now slowly inflate the balloon. As the balloon expands, every dot moves farther away from every other dot. None of the dots are actually crawling across the surface. Instead, the surface itself is stretching, carrying the dots along with it. This is roughly what happens in the universe. Galaxies are embedded in the fabric of space, and as space expands, the distance between galaxies increases. Because of this expansion, the distance to a galaxy is not a fixed number that stays the same forever. It changes with time. This leads to a strange question for astronomers. When we measure the distance to a very distant galaxy, what distance are we actually talking about? The light we observe today may have left that galaxy billions of years ago. At the moment the light began its journey, the galaxy was closer to us because the universe was smaller. But while the light was traveling through space, the universe kept expanding. By the time the light finally reached Earth, the galaxy had moved much farther away. So there are several different ways to describe the distance. One distance describes how far away the galaxy was when the light first left it. Another describes how far the light actually traveled while space expanded beneath it. A third describes how far away the galaxy is today after billions of years of cosmic expansion. Each of these definitions gives a different number. This means that in cosmology, distance is not a single simple concept. It depends on how the measurement is defined. Two astronomers might describe the same galaxy using different types of distance, and both could technically be correct depending on the method being used. The deeper scientists look into the universe, the more this complexity grows. At extremely large distances, the expansion of space becomes one of the dominant factors shaping what we observe. The light arriving in our telescopes today has often traveled for billions of years through a universe that has been constantly changing during that journey. So when astronomers measure distant objects, they are not simply measuring space as it exists now. They are interpreting signals that were created in a universe that looked very different from the one we inhabit today. This realization forces scientists to think carefully about what the word distance really means when applied to the largest scales of the cosmos. Even after developing clever tools like Parallax and Cepheid variable stars, astronomers eventually reached another limit. The universe extends far beyond the range where individual stars can be studied clearly. At those enormous distances, stars blur together, and entire galaxies appear only as faint smudges of light. Measuring distance in this regime requires a different approach. Astronomers began searching for events in the universe that behave like extremely powerful and predictable beacons. One of the most important discoveries in this search was a special type of stellar explosion known as a type of supernova. A supernova is the violent death of a star, releasing an enormous amount of energy in a short time. For a brief period, a single exploding star can shine as brightly as an entire galaxy containing billions of stars. This brightness allows astronomers to observe these explosions across vast distances in the universe. Type I supernovae are particularly valuable because they occur under very specific conditions. They happen in systems where a dense stellar remnant, known as a white dwarf, pulls material from a nearby companion star. As the white dwarf gathers more and more mass, it approaches a critical limit. When that limit is reached, the star becomes unstable and undergoes a sudden thermonuclear explosion. The remarkable feature of this process is that the explosion tends to happen at nearly the same mass every time. Because of this consistency, the resulting supernovae reach nearly the same peak brightness. In other words, these explosions behave like standard candles, objects whose true brightness is known. When astronomers detect a Type A supernova in a distant galaxy, they measure how bright it appears from Earth. If it appears very faint, they know the explosion must have occurred extremely far away. By comparing the observed brightness to the known intrinsic brightness, they can estimate the distance to the galaxy where the explosion occurred. Using these supernovae, astronomers extended their measurements far beyond the reach of Cepheid stars. Distances could now be measured across hundreds of millions and even billions of light years. This method played a crucial role in one of the most surprising discoveries in modern cosmology. In the late 20th century, astronomers used Type I supernovae to study extremely distant galaxies in order to measure how the expansion of the universe was changing over time. At first, scientists expected that the expansion of the universe might be slowing down. Gravity from all the galaxies and matter in the universe should gradually pull everything back together, reducing the expansion rate. But when astronomers carefully measured the distances to distant supernovae, the data revealed something unexpected. Those galaxies were farther away than predicted. The only explanation that fit the observations was that the expansion of the universe is not slowing down. Instead, it is accelerating. Something in the cosmos appears to be pushing space itself apart more and more quickly. Scientists call this mysterious influence dark energy, but the name does not explain what it actually is. It simply describes a phenomenon that we observe, but do not yet fully understand. This discovery shows how deeply distance measurements shape our understanding of the universe. By carefully measuring how far away things are, astronomers uncovered evidence that the cosmos is expanding faster over time. Yet even with powerful tools like supernova measurements, uncertainty remains. These techniques rely on assumptions about how explosions behave, how light travels across enormous distances, and how dust and intergalactic matter might affect the brightness we observe. Each measurement contains small uncertainties, and when scientists try to map the largest structures of the universe, even tiny errors can grow into significant disagreements. This is one reason why measuring cosmic distance remains one of the most challenging tasks in astronomy. When we step back and look at all these methods together, something interesting becomes clear. Measuring distance in the universe is not done with a single tool. Instead, astronomers rely on a chain of techniques, each one extending a little farther than the previous one. This chain is often described as the cosmic distance ladder. The name is quite appropriate because each method depends on the reliability of the one below it. If the lower step is even slightly inaccurate, that error carries upward through the rest of the ladder. The first step, parallax, works only for relatively nearby stars. It provides a geometric measurement that does not rely on assumptions about brightness. Because of this, parallax serves as the foundation for calibrating other techniques. Once astronomers know the distances to nearby stars through parallax, they can determine the true brightness of certain stars like Cepheid variables. With that information, Cepheids become reliable distance markers for much larger regions of the galaxy and for nearby galaxies beyond the Milky Way. After that, the brightness of Cepheid stars helps calibrate even more powerful tools, such as Type Ia supernovae. Those supernovae allow astronomers to estimate distances across enormous cosmic scales, reaching galaxies billions of light years away. Each step expands the map of the universe, but each step also carries a subtle risk. If one layer contains a small mistake, that mistake affects the measurements built upon it. Because of this, astronomers constantly recheck and refine every rung of the ladder. In recent years, this careful process has revealed a puzzling disagreement in cosmology. Different methods of measuring the expansion rate of the universe are giving slightly different answers. The expansion rate is often described using a number known as the Hubble constant. This number tells us how quickly galaxies are moving away from each other as the universe expands. One way to estimate the Hubble constant is by using the cosmic distance ladder. Astronomers measure distances to galaxies using Cepheid stars and supernovae, then compare those distances with the speed at which the galaxies appear to be moving away from us. Another method looks much farther into the past by studying faint radiation left over from the early universe. This radiation, known as the cosmic microwave background, provides a picture of the universe when it was extremely young. By analyzing patterns in that radiation, scientists can infer the expansion rate indirectly. Surprisingly, these two methods do not produce exactly the same number. The difference is small, but it is large enough that it cannot be easily ignored. Some researchers suspect that the disagreement may come from hidden errors in measurements. Others wonder if it might be pointing toward new physics that we do not yet understand. This situation illustrates how delicate cosmic measurements really are. Astronomers are attempting to measure distances across billions of light years using tools that depend on light signals that have traveled for immense spans of time. Even tiny uncertainties can grow into significant differences when applied to such enormous scales. Yet despite these challenges, the cosmic distance ladder has allowed humanity to construct a remarkably detailed picture of the universe. It has revealed the existence of countless galaxies, mapped the large-scale structure of the cosmos, and helped scientists understand how the universe has evolved over billions of years. Every improvement in measurement brings the map into sharper focus, while also reminding us that our understanding is still incomplete. The deeper we look into space, the more we realize that measuring distance is not simply a technical problem. It is also a window into how the universe itself behaves, and into how much we still have left to discover. When all of these ideas are put together, a very unusual picture of the universe begins to appear. Measuring distance in space turns out to be far more than a simple task of placing numbers on a map. It becomes a way of understanding how the universe itself unfolds across time. On Earth, distance usually feels like a straightforward concept. If you walk across a field, you know how far you have traveled. If two cities are separated by hundreds of kilometers, that distance stays essentially the same tomorrow as it is today. Our everyday experience teaches us that space is stable and distances are fixed. But when we look outward into the cosmos, that familiar idea starts to break down. Light does not reach us instantly. Every beam of light takes time to travel. Even light from the sun requires about 8 minutes to reach Earth. When we observe the sun, we are already seeing it as it existed several minutes ago. When astronomers observe objects much farther away, the delay becomes enormous. Light from nearby stars may take years or decades to arrive. Light from distant galaxies may travel for millions or billions of years before reaching our telescopes. This means every observation of the universe is also an observation of history. A telescope does not simply show us where objects are located. It shows us what they looked like when the light first began its journey toward us. The deeper we look into space, the further back in time we are seeing. Some of the most distant galaxies we observe today emitted their light when the universe was extremely young. That light has been traveling across expanding space for billions of years before finally arriving at Earth. By the time the signal reaches us, the galaxy that produced it may have changed dramatically. New stars may have formed, old stars may have exploded, and entire regions of the galaxy may have evolved in ways we cannot yet see. In a sense, astronomy allows us to study multiple moments in cosmic history all at once. Nearby stars show us relatively recent events, while distant galaxies reveal ancient chapters of the universe's story. This realization changes how we should think about the night sky. What appears to be a quiet and unchanging pattern of stars is actually a complex mixture of signals from many different times. Every star in the sky is sending us information from a particular moment in its past. Some of those moments occurred a few years ago. Others happened before human civilization even existed. Distance in this context becomes closely tied to time. When astronomers measure how far away something is, they are also measuring how long its light has been traveling. A galaxy 1 billion light years away is not simply located far across space. It is also connected to a moment 1 billion years in the past. The universe therefore acts like a vast archive of light, preserving records of earlier stages of cosmic evolution. Human beings occupy a small location within this enormous structure. We are observing the universe from one tiny planet orbiting one ordinary star among hundreds of billions of stars in our galaxy. And yet, using careful observation and patient reasoning, we have managed to reconstruct much of the universe's story. We have learned that galaxies exist far beyond our own. We have discovered that space itself expands. We have measured distances that stretch billions of light years across the cosmos. Still, the deeper we investigate, the more we recognize that our measurements are only approximations. The universe is vast, dynamic, and filled with processes we are still struggling to understand. Perhaps the most remarkable aspect of all this is that the faint light reaching our eyes each night carries information across unimaginable distances and times. When we measure those distances, we are not simply mapping space. We are decoding messages from the past. The night sky is therefore not just a display of distant lights. It is a record of the universe gradually revealing its history, one photon at a time.